Okay, let's get started today. We are going to be finishing up with binary search trees today, and then we're going to be going into AVL trees. So what we're going to be doing with binary search trees is we're going to be considering the deletion operation, and then with AVL trees we're going to be considering what are called balancing or tree balancing operations, where we're trying to keep the number of nodes in the left subtree roughly equal to the number of nodes in the right subtree. And after today, you'll be able to complete Lab 10, plus you'll be able to make good progress toward Lab 11. So we're going to spend 2 days on AVL trees. Originally, I had us just with 1 day, and after looking at the material, I decided it's complicated enough that we need to kind of go through it at a slow pace. Want to give you some exercises with them, so we're going to take 2 days to go through it, which is no problem because if you'd looked at the syllabus, we had no lectures planned for the last week of classes, and we still don't have a lecture plan for the very last day. Now, we may end up having a lecture on the last day, so we're completely on schedule. We have plenty of time, so don't worry about the fact that it's now a 2-day lecture rather than a 1-day lecture. Okay, so you should have gone over the printing code yesterday in lab, the in-order printing. Is that correct, Alan? Fantastic. Okay. So what we have left to consider today for binary search trees is the delete operation and the recursive destruction of the tree when we're done using it. So we'll start with deletion, which is the trickiest of the 3 operations to implement. In general, it also is going to take order and time. And there's 3 cases to consider with deletion. So I'm just going to walk us through the 3 cases first. Then I got a couple exercises for you to do with deletion to see if you got it, and then we'll go through the code. So consider this tree that we have here. And as I said, there's 3 different cases with deletion. So the simplest case is when the node that we're deleting has no children, okay, which means we are deleting a leaf. Okay, that's case 1. It's a leaf. And it's the simplest case because we simply delete the node. And when we're done, still a binary search tree. Okay, it should be pretty easy to see that if we delete Callista from this tree, voila, still a binary search tree, right? Okay, so second case is the one where we have a single child, okay? So one example here is if we delete Binky, okay, the root of the tree. Looks kind of nasty. We're deleting the root of the tree. But Binky has only one child, which is Fred. And so we simply replace the node we've deleted with that child. So in this case, Binky gets replaced with Fred, which is what you see in this frame right here. Okay, so Fred just becomes the new root of the tree. As a second example, let's say that we want to delete Daisy. So Daisy's right here. Daisy has a single child, Callista, and if we replace Daisy with Callista, okay, so Callista kind of comes up here to replace Daisy. We get this situation right there. And again, you see we're still satisfying the restrictions of a binary search tree because if we were guaranteed, basically the situation is, let's say that we have, here's our root, here's the right subtree. Let's say here is the node that's being deleted, and let's say that it has one child, and I'll just put here question mark because it doesn't matter which of those two is the child. What we know is that because whatever this is in the left subtree, we know that it has to be less than this parent. So if let's now get more specific and just assume that the child is over here. We know that whatever we have less than is less than the key right here. Therefore, if we move the question mark up to there, it's still less than the key, and we've reestablished our binary search tree condition. Okay? So, those are the easy cases. The hard case is when we have two children and we do a deletion. So let's say that we delete Fred from this tree, and now it's not clear what to do. Okay, it's sitting there right in the middle of the tree, has two rather significant subtrees sitting under it. So we arbitrarily make a decision about what to do. And in this case, well, not an arbitrary decision. We're either going to delete the largest value in the left subtree or the smallest value in the right subtree first. And then we're going to replace Fred with that node. So we're going to, in this course, assume we're deleting the largest element from the left subtree. So I'm going to put here first delete the smallest, the largest key from the left subtree. And once we've done that, now we replace the deleted key. Need to be clear. Replace the key that we are deleting with the key with the largest key from the left subtree. Okay, so the question is, why does this work? Okay, so let's think about it for a moment. What is going to give us confidence that this strategy will leave us with a binary search tree? Okay, so if we delete the largest key from the left subtree, which, eyeballing it, what is the largest key in Fred's left subtree? Fiona. Can we definitively say that if we put, so we're saying in 2 we're going to replace Fred with Fiona. That's what 2 says. So do we definitively know that when we do that, that every key in the left subtree will be less than Fiona? Yes, why?
Because you picked it, so it would be the greatest.
Yep, I picked it. I stacked the deck, right? I picked it so it would be the biggest key or largest key in the left subtree. So by definition, it's got to be greater than anything else in the left subtree. Okay? So is it less than everything in the right subtree? Yes, why, Doug?
Because its key is greater than
But if it's greater than everything else, shouldn't it be greater than everything in the right subtree? We're just saying it's actually less than everything in the right subtree. No matter what key I pick from the right subtree, my claim is it's less than.
Because it's already in the left subtree.
That's right, because any key in the left subtree, by definition, is less than any key in the right subtree. That's a fundamental property of a binary search tree. So we're guaranteed that if I promote any key from the left subtree to the root, we're guaranteed that it has to be less than any key in the right subtree. So 2, we're absolutely guaranteed that if we replace the Fred with the largest key in its left subtree, that we will still maintain the binary search tree property. So the next thing becomes, how can we be so sure that we can delete the largest key in the left subtree without also having a problem that it has 2 children? It's going to be very easy if it has only 1 child or if it has no children, but we've already seen that if it has 2 children, then it's going to be problematic. So why are we guaranteed, why does 1 guarantee us that we can't have 2 children? What if it did? What if we picked, so what if Fiona had a right child? Why do we know for a fact that that's impossible?
Because since it's to the right, Fiona's going to be greater than Fiona.
Exactly. So if Fiona had a right child, then we know that that right child would have to be greater than Fiona. Someone give me a name between I and R with an F. It's got to be an O.
Ollie.
Fonzie, there we go. Someone watched Happy Days.
He said it's gotta be an O.
What?
Oh, with an O.
With an O.
Start with
You gave me an A.
Ollie's actually
Oh, Ollie, you're right. So I could have said Folly. Doug's Folly. No. Okay. So, but the point is, if Fiona had a right child, then we had not selected the largest key in the left subtree because we had a key greater than Fiona. So if we choose the largest key from the left subtree, we're absolutely guaranteed that it cannot have a right child. So if I move over here, this condition guarantees that the largest key in the left subtree, we know that the largest key in the left subtree cannot have a right child. Okay? So instead of saying this condition, we will say the largest key in the left subtree cannot have a right child. Is that clear? Everyone agree with that? So that makes deletion easy for that node. It makes it one of the first 2 cases. Okay, here we see that Fiona does have a left child, but deleting it is no problem because we simply replace Fiona with Ernie. Okay, so the deletion of the largest key in the left subtree now frees it up to replace whatever key we actually want it to delete. Okay? So does that make sense? You all think you can do this yourselves? Well, we shall see. Okay? So everyone got this written down? Okay. Let's see if he had I have my own examples. Okay, first do it with this one. That's no good. He already told you the solution. Okay, so here he's deleting Luther. And in this case, it's pretty trivial because the largest key in the left subtree is I still can't say it, Luigi. And we delete it, goes away, and then we simply put Luigi here. Okay, so that's a pretty simple one. Okay, let's go to my examples. So if you actually go to my web page, my lecture notes, and you go to the bottom, you'll actually see that I have a link called BStree deletion and AVL rotation exercises. And, whoops, wait a minute. Okay, this shouldn't have said rotation. This should have said BStree. So, modulo that. So what I want you to do is delete John from this BST tree. Okay, so take a moment, figure out how you would delete John. I'm going to give you about a minute because this is pretty simple.
We don't have to write delete for the.
No, I'm not asking you to write
I'm
code.
talking about for
Sorry.
lab A.
Oh. Do what?
We don't have to write delete for lab A, do we?
No.
It's already written.
Right. You don't have to write. You don't have to write insert, delete, or find for lab A.
So why are you saying that we should write
Oh, what you will have to write is two functions called isAVLTree and rotate. And those functions you don't know how to write yet
We've said,
in lab A.
so those have nothing to do with deleting.
They don't have anything to do with deleting. Sorry.
It is
If I probably didn't quite say it right. Okay, so man in orange, yes, you. What is the tree going to look like? What am I going to do in order to delete John?
You're going to delete John and then you're going to move Jill where John is.
Very good. So John goes away, Jill moves up, and that's what the tree looks like. Okay, questions about that? Relatively easy, right? Okay, let's make it harder. Now I want you to delete Laura. Again, this is a BST tree. I'll have to change that. So I want you to delete Laura. Again, I'm going to just give you about a minute. It's not a very difficult one. Okay. So, Senior, I'll let you have a crack at
Well,
this.
since John is the biggest key in the left subtree, so we're
Very
going to
good.
instead of Laura.
Yep, so we're going to, John is the biggest key in the left subtree, so we're going to replace Laura with John, and
Well, Brad is still less than John, so we can leave it like this, and Jill is still bigger than Brad, and Patrick is still less than Brad, so we can just replace Jill with John.
that's right, actually replace John with Jill. Very good. So we delete John, which is what we did in the previous slide. So Jill gets promoted to become the right child of Brad, and then we replace Laura with John. Okay? This makes for a very nice final exam problem. So, are we all comfortable being able to do this? Can almost guarantee an exam problem like this. Okay?
Good question.
Mm-hmm.
On an exam, would you be alright with us taking the easier option of moving Maria after Laura instead?
Not really, because you have to, so you find that easy to eyeball it, but a computer doesn't. A computer, you kind of have to give it a fixed strategy to always do it. So I would actually, on an exam, want you to always do it out of the left one. But that's a good question. Certainly it's easier to do it this case with Maria, but that's only because we can eyeball it, and a computer can't eyeball it as easily. Other questions? Yes.
So we only use the greatest. So we only use the greatest node on the left tree simply for just to have a set convention.
Just have a what?
A set convention.
Yes, just to have a set convention. You could flip a coin. Theoretically, you could flip a coin, right? If you have a lot of deletes, it actually turns out that you could get a somewhat unbalanced tree by doing this, because you would always be deleting out of the left subtree. But it's actually, in practice, it's fairly rare to do deletions instead of insertions, so it just turns out to be more trouble than it's worth to, in effect, flip a coin. You could generate a random number and say if it's less than 0.5, we'll go down the left subtree, and if it's greater than 0.5, we'll go down the right subtree. So if you really want it to be fair, that's what you would do, but it makes it easier to just follow a set convention. Okay. Other questions? Okay. In that case, let's take a look at the actual code for implementing delete. Mm-hmm.
If you want to delete something from the right subtree, you need to find the smallest node.
No, okay, good question. So Senia's saying, but what happens if we, like here, Fred is in the right subtree. So we still, if we delete Fred, we still are looking for the largest key in its left subtree. Okay, in that case it's Ernie. Okay, so moving on. Any other questions? I don't mean to rush it. Happy to take questions. Yes?
And the one you were just looking at, since it doesn't have a left tree.
Just see, just a sec. Which one? This one or?
The one you like literally just said.
Okay.
Um,
Not that one. This one.
yeah. So if you wanted to delete Binky, would you take the biggest from the right, or the smallest from the right? I mean.
No, in this case, Binky has only one child, so that's the easy case where we simply replace Binky with its right child.
Oh.
Okay, so actually, let's see, right here. So remember this tree, and if we delete Binky, this is what happens. After deleting Binky, we just replace it with it. So that's the easy case. Even though it has a monster right subtree, it doesn't matter. The fact is it doesn't have a left. So perhaps a better way to say it is if it doesn't have, if it has only one subtree, you simply replace the node with that subtree. Okay. I won't give you a question like that on the exam because it's too easy. Okay, other questions? Actually, I did it once by mistake, but that was many years ago. Other questions? Okay. So, coming down to the delete. So, as always, the first thing that we need to do is we need to locate the node we wish to delete. So we just do, in essence, a find. And, of course, we first must check to see whether we actually found the key. If we terminate our search because we reached the Sentinel node, then we return 0 to indicate that the key was never in the tree. So we're saying the delete failed just because the key was never in the tree. Otherwise, we need to locate the node's parent, and we're going to be doing some hooking in, because remember, in most cases, we're going to be moving some child up, and that child is going to have to be hooked in to the parent. So, first thing we do is we check to see if the left child of n is empty. So if we have this case, okay, so n has no left child, that's what we're checking. If so, what we're going to do is delete n. So actually we should, here's our parent. Okay, in fact right now we don't know whether we're a right child or a left child, so I'm putting n directly under it because we don't know whether n is a left child or a right child right now. But what we're going to have to do is reorient this pointer so that p now has this pointer to its right subtree. Okay, and this code right here is checking to see whether n was a left child or a right child. So if n, the first case, is that n was a left child, like this. Okay, so in that case, we have to make the parent's left point down here. Okay, so it points to n's right child. That's all we're doing with this code. We're making parent's left point to n's right. Otherwise, n was a right child. If I could ever erase it. So the situation looked like this. And now we're making p's right point down there like that. So that's this case right here. So now we've got the link, we've linked the right subtree up to p. Now we need to make the right subtree its parent pointer needs to point to p. So that's what this statement right here is doing, is making the right subtree's parent pointer point to p. Now we have effectively removed n from the tree, right? Because this link is gone and this link is also gone. So n has been isolated, so we can now delete it, and we have to remember to delete the size by 1. Okay, so that takes care of our case with if it is the, if there is no left child. If this case fails, then we know we have a left child, right? Do we agree with that? If this case fails and we get down to here, we know we have a left child. Do we agree with that? We have a left child. So now we check to see if we have a right child. So this check says, actually, do we not have a right child? Do we have the situation where we only have a left subtree? If the answer is yes, then we do the same thing we did before, except now we're making the parent, we're figuring out how to link the parent with the left subtree, and we're also making this left subtree's parent pointer go up to P. So it's the same code we had before, just kind of a mirror situation. I'm not going to go through it because it's just a mirror situation to what we had a moment ago. Okay? So now the only difference is that we had the only child being a left subtree. We're promoting that left subtree to replace n. So questions? I'm happy to go over it if there's a question. Okay? Wow, I'm getting a lot of mail from a lot of stuff that should be going to my junk folder. Okay. So, if we get down to here, okay, then, whoops, that's not right. If we get down to here, just a moment. Yep. So if we get down to here, then we have the third case where we must have both a left and right child. Okay? So in that case, the first thing that we're going to do is we're going to try to find the largest key. So this code right here is going to find the largest key in left subtree. Okay, so how do we do that? Well, we start by going to the left subtree. So we start our search by going to the left subtree. So here's n. We need to go to the left subtree. So right now, MLC points to the left subtree. And now, to find the largest key, we chase down the right side. Right? We always follow the right link. Because the right link is always, or the right child is always greater. So we always follow the right link until there is no further right link to follow. Eventually we come to a point where possibly that node has a left subtree but has no right subtree. And at that point, we know that we have found the largest key in the left subtree. Right? So we always chase the right child, because the right child is always greater than the node that we're at, right? And when we finally reach a node that has no right child, well, even if it has a left child, it's greater than everything in that left subtree. So we must have found the largest key in the left subtree. So that's why we simply keep setting MLC to the right node, and we stop when the right child is the sentinel. Because now we know that we're pointing to the largest key in the left subtree. Okay, so at that point, we simply save the key and value from that one. Then we wow. That is, oh, okay. Yep. Then we call delete. So we're actually calling the delete method. to delete this key. So it's basically a recursive call to delete. So delete the largest key in left subtree. Okay, so that's just a recursive call, and we know that it's going to succeed easily because it has at most one child. And then we assign to n, so we don't actually delete n, instead we just replace n's current contents with the contents of that largest key. So the node that actually gets deleted is the node that contained the largest key in the left subtree. And can anyone tell me why I had to do this? Why couldn't I just say n key equals two different things? Why couldn't I, first of all, just say here n key equals MLC pointer? Why, and take these two out? Why was it necessary to save the key and the value? So what do you think MLC points to after we come back from the delete? Who knows? Very good, Gerald. Because we delete it, the delete function deleted the node that MLC points to. So when we come back from delete, MLC, we have no idea what it points to. There's a good chance we'll segfault if we try to go through MLC at this point. That's why we had to save the contents of MLC before we called delete, because the whole point of delete is to delete the node that MLC points to. Does that make sense? You've got to be careful with this. Remember, with pointers, you never want to be referencing stuff that a pointer points to after what it points to has been deleted. Bad news. Yes, Scott?
How does your delete work here? Because all you give it is a string.
Right.
You
So,
don't specify if it's in the tree or anything.
but I know it's in the tree because,
But how does it know to go to the tree and delete it?
okay, so what happens, this is a recursive call to delete. So this right here is a recursive call to this delete function.
Oh, okay.
Okay? So what it does is it goes ahead and refines that node.
Yeah,
So it's a
okay.
little, you could argue this is a little inefficient
I just thought it was
because,
the other delete.
no,
But
it's
okay.
this delete. Yeah. That's why when I first saw it, I also went, whoa.
Yeah.
And I was thinking he was calling the delete, and then I remembered, no, this is a recursive call to delete.
Okay.
Okay? So, the next question is you're thinking, well, this is silly. So, Brad just said, why do I have to save them? Why doesn't he just move these two statements up here? Right? Why not just say, instead of temp, why not just up here say n key, do the replacement, n key equals MLC key, and n val equals MLC val. Why does Dr. van der Zanden go to this big issue of saving those values, then doing the delete, and only after the delete does he put the values into n? Why not just do it immediately? Yes, Doug?
Because you lose the values of n.
Yep. Well, you certainly lose the values of n, and why is that bad? You certainly lose them, but why is that bad?
N is going to be your new. You're putting n where you're deleting, like n goes in your new spot.
Okay, so it's certainly, okay, so let's do it. Let's show what happens. Let's do a clear example. So let's go up here back to Fred. Okay. So let's say here we got MLC points to Fiona. Okay. But before we called delete, we replaced Fred with Fiona. Okay. The problem is now we call delete on what? We call delete on Fiona, right? If we look at the code here, wish it didn't have to. Right after, if we do the assignment and say n key equals MLC key, what we've done is we've assigned Fiona to MLC, but now this is saying delete Fiona. Okay, so if we go back up here, we already replaced Fred with Fiona. Whoops. There, we replaced Fred with Fiona. So now when we do the delete, we try to delete this node right here rather than this node right there. We're deleting the wrong node. So the problem with doing a premature replacement of Fred with Fiona is that when we call that recursive delete, the delete is going to zero in on the wrong node. So we have to wait until we have actually deleted this node before we put Fiona in place of Fred. So this is a case where it's very important to do the operations in the order that you see them down here. This order is super important. You have to do it in exactly that order or things go wrong. Okay, why am I harping on this? I'm harping on it because I want you, when you write your own code, to be very careful about making sure when you're deleting stuff, especially deleting pointers, that you do things in the right order. Because not doing things in the right order, as you see here, can easily lead to seg faults or logic errors. So with pointers, oftentimes order is everything. Operations are not commutative. And doing them in different sequences leads to radically different outcomes. So here it's like going through a swamp. There's only one right way through the swamp. Okay? Take another way through the swamp and you will sink. Okay? Now, I know that this was kind of a long explanation, but it seems that we might have missed a case here, right? I considered the case where a node has a left or right child, and I considered the case where a node has two children. What case do I appear to have missed?
It has no children.
If it has no children, I never had a statement that you would think that I might have had a statement that says if n left equal sentinel and n right equal sentinel, okay, then do stuff for case 1 where n is a leaf. But there's no such code. Is that a logic bug? It's not. Okay? Let's see why it's not a logic bug. It's actually being handled by one of these three statements. And it's actually being handled nicely right here. So if n left is equal sentinel, this condition is true, right? So we come into this code right here. Okay? And we set the parents left or right to whatever the right child is. Well, if the right child is the sentinel node, we simply set the parents left or right to the sentinel node, which is in fact what we need to do. If we have something like, say, Binky goes to, say, Alfred, and we're deleting Alfred, and Alfred's a leaf node, what should Binky point to? What should Binky's left point to when Alfred gets deleted? Sentinel node. So this code naturally handles the case where the right child also doesn't exist. Now, you could reasonably say, well, wait a minute, what's happening here? Because you're still going ahead and you're making n's right, which, quote, doesn't exist, point to the parent. But what am I really doing with that statement? What is n right in this case? It's the sentinel node. So I'm making the sentinel node's parent, and I'm setting it equal to parent. Well, it's one of those cases of big whoop-de-doo. We never use the parent field for the sentinel node. It's just a throwaway field. We never use it, so it's safe to change it. It's just taking advantage, it's a trick. We're taking advantage of the fact that we never use the parent node or the parent field in the sentinel, so it's okay to change it to whatever our heart desires. It's just like that trick I showed you last time where I set the key of the sentinel to be the key we want it to find. And I said it's fine to do that because the sentinel node technically is not part of the tree. So in fact, we're doing just fine by allowing us to set the sentinel node's parent to parent. We go ahead and delete n, so Alfred goes away, size gets decremented. We actually handled case one, just it's a cute little trick. Okay, yes, Alan?
Seems a little unsafe though, in case somewhere else in the code we also made a decision that since we're not using a parent node, we can use it for some other purpose, and if that purpose is to be consistent throughout.
Yes, sometimes we hang ourselves. That's why sometimes clever code ends up, yes, you are right. So sometimes clever code like this could end up, you really do have to kind of, it probably would be very good in this case to state the assumption explicitly. Remember we talk about comments, and in this case it would probably be very good if in the comment block we made it very explicit that we are assuming that the sentinel node's parent is a safe thing to assign to, okay? Because it's an important assumption. So this is where a comment can be invaluable. And also, it's invaluable, a comment to say, hey, the case one where it's a leaf node, it may look like we're not handling it, but actually we are, and this is how we're doing it, okay? So this is exactly where you would want a comment to explain something that's not obvious. So other questions or comments? Okay? So that's how delete works. After all that, it may be a relief to know that the recursive destroy in the destructor is very simple. Okay? So the destructor, we're simply destroying the tree, which means we have to destroy all the nodes in the tree. And to do that, it's a very simple recursive algorithm. We call recursive destroy on the sentinel's right, which is the root. In the destroy, if we've reached the sentinel, then we return because we have reached a non-existent child. Otherwise, we first destroy our left subtree, then we destroy our right subtree, and once we've destroyed both our left and right subtrees, it's safe to destroy ourselves. So, for example, if I am here and I'm Fiona, I first destroy my left subtree, then I destroy my right subtree, and then I delete myself. Why is it not safe to put the delete here? Why can't I make it the first thing I do?
You can't get to the children.
Yep, very good, Gerald. If I make the delete first, okay, so I have Fiona, and I delete it first. Oops, there goes my pointers to the left and right subtrees. When I try to access the left field of n, there's a good chance that I segfault because n just got destroyed. So I have to destroy n at the very end. It's for the same reason that I have to wait to the very end to destroy the sentinel. Because I might reach the sentinel node, in fact I will reach the sentinel node at different times during my recursive destroy. And what kind of traversal do we have here? Let's get a show of hands. So we have three types of traversals. We have pre-order, in-order, and post-order. Okay, so how many think that we are doing a pre-order traversal? Raise our hands. No one. Okay, big position. Okay, how many think we're doing an in-order traversal? No? Still no takers. How many think we're doing a post-order traversal? Hey, why is not everyone's hand up? That means some of you aren't voting. Okay, you're going to have to vote on the exam. Okay, so for all of those who voted for post-order, you are right. So we first, remember a post-order traversal is one where we first process our children, and only after we've processed our children do we do something to ourselves. So here we process the children first, and then we processed ourselves. Okay? I do so love asking questions like this on an exam. So if you didn't vote, just remember you will vote on the exam. Actually, you don't have to vote on the exam either. Little secret, as instructors, we love it when you don't answer a question. Saves us time. Okay? Doesn't work out well for you, but saves us time. Okay, the other one was the sorted vector. So we wanted to do a traversal of the tree and return all the values of the tree in sorted order by key. Remember, that was one of the big advantages of the tree, was that we could get the keys back in sorted order very easily. So that's what the sorted vector does. And it's very easy. If we have, again, Fiona, and a left subtree and a right subtree, and we're creating our vector, should be fairly obvious. Here's left, here's right. It should be fairly obvious that everything in the left subtree goes to the left of Fiona, then Fiona goes into our vector, and finally everything from the right subtree goes into the right side of our vector. Right? If we're doing a sorted vector, does that make sense? Everything from the left subtree in the left of Fiona, everything in the right subtree to the right of Fiona. So that means that when we do our recursion, again, our base case is if we're at the sentinel, we return. Otherwise, we first recursively call make vector on the left subtree to put all the values from the left subtree into the vector. That achieves this. Then we call array push with the value. That puts Fiona, actually it doesn't put Fiona in, it puts Fiona's value in here, whatever value we associate it with Fiona. And finally, this this recursive call puts all the elements from the right subtree in there. Okay? Very nice. Let's do some more voting for in order, pre-order, or post-order. So, how many vote for pre-order? Is this a pre-order traverso? Okay, good. We have one vote. Okay, this is like voting for, say, in the NCAA tournament, voting for our 16th seed. Okay, but might have a big payoff. Just saying that because you're the only one taking the position. Okay, how many for in order? Okay, a lot of you voting for Kentucky. Of course, Kentucky did get upset. And post order. How many for post order? So it is, in fact, in order. Okay, because we first visited the left subtree, then we processed the node, then we visited the right subtree. I assume you're just playing around.
Says it up there.
Okay, but at least it didn't say it on the notes, did it? Oh, it did.
Yeah.
Oh well, there we go. Shows how awake I am. Have to get it off of there next time. Okay, maybe I was going to disagree with him. Of course, then I'd be wrong. Okay, any questions about any of this? About binary search trees in general? Okay. So that moves us on to AVL trees. Okay, so AVL trees are one of a type of what we call balanced trees. So with balanced trees, we are trying to ensure that, roughly speaking, the number of nodes in the left subtree is equal to the number of nodes in the right subtree. We don't have to make it exact, so number of nodes in left subtree is roughly equal to the number of nodes in the right subtree. Okay. It turns out it would be well, first of all, let's just show you why we might want to balance things. If we do a set of numbers and we insert them like this in sorted order into a binary search tree, 3 becomes the root, then 6 becomes the right child, 9 becomes the right child of 6, 12 becomes the right child of 9, 15 becomes the right child of 12, and you can see we have a very unbalanced tree. So the problem with binary search trees is if we have a bad insertion order, such as we insert in sorted order, then our operations become order n, and that's no good. So if our insertion order is bad, our performance drops from order log n to order n, and we don't like that. So oftentimes it is the case that binary search trees work well because a lot of data is pretty random, and without trying to do any kind of balancing, the tree will automatically be roughly balanced. If the data is random, we can use a binary search tree, because we can be pretty sure with random data that the tree will be pretty balanced. But if we have some reason to suspect that the data might not come in balanced, then we may want to be more careful and try to use some balancing algorithm. For example, if I have names from the alphabet, do you think that all letters have an equal chance? Do you think that if we look at names, that each letter has an equal chance of being the first letter in a name? No. Okay, we all are pretty sure that X isn't going to have as many first names as S. Okay, I think S has the most or largest number of first names. I used to do, this was back in the day when we didn't have computers and my dad was a textbook author. I used to have to, he'd put his references on index cards, 3x5 index cards, and I had to sort them into piles. I just remember that the S's were huge. Okay, so were the M's. The M's and S's were the two biggest piles. But we know that if we're inserting names, it's not random. So we may run into this issue that we could get an unbalanced tree, especially because M and S are both toward the back of the alphabet. So in fact, names tend to be backloaded toward the back of the alphabet. So we need to try to get balance. So requiring that there be exactly an equal number of nodes in the left and the right subtree is too onerous. Okay, first of all, it would require that we have an even number of nodes. We could never have an odd number of nodes, right? We have to have it the same. So you can immediately start to see some problems. So that's too rigid. So we want to come up with something where they're close. And AVL trees, their condition, their balance condition, is that for every node in the tree, so for every node in the tree, the heights of its two subtrees differ by no more than 1. So we're not requiring exact balance, but we are requiring that for every node in the tree, the heights of its two subtrees differ by no more than 1. Okay, so they'll be close. Okay, so let's take, by the way, AVL, name for its 3 creators. I can't get it off the top of my head, but the last names of the 3 creators started with A, V, and L. Hence AVL trees. So invent your own tree and get your name on it. Yes, Doug. Really?
Yeah, one of them had like a hyphenated last name.
Ah, thank you. So who were the 2 creators?
Georgie Adelson Belsky and E.M. Landis.
Okay. There we go. For Jeopardy. CS Jeopardy. Okay. So let's take a look at some of these AVL trees. There we go. So here we see some AVL trees. So any tree that has a single node is an AVL tree. This tree right here, if we consider its height, remember the height of an empty tree is -1. So the height of Binky is 0. The height of a leaf is 0. The height of an empty tree is -1. So Eunice's 2 subtrees differ by no more than 1. Here, the height of both of Eunice's subtrees is 0, so that's certainly true. Here, we have to look at each node, so let's just do heights. This is 0, this is 1, this is 2, this is 0. So for Binky, the heights of its 2 subtrees are 0 and -1. So we check off Binky. And for Eunice, the difference in heights is 1. So we check off Eunice. So that's an AVL tree. Here's our most interesting one. So again, let's just put in our heights. For Leafs, it's always 0. For Daisy, what is Daisy's height? 1. What is Binky's height? 2, which is the greater of its 2 children. Fred is 1. Eunice is 3. So again, we look at each node. We never bothered to look at Leafs. Leafs, by definition, satisfy the balance property. Okay? So Daisy, she balances or is okay. So Daisy's subtrees differ by at most 1. If you look at Binky, its subtrees differ by at most 1. Fred's subtrees, there's a -1 for its left, so it balances. And Eunice, its 2 subtrees differ by at most 1, so it is an AVL tree. Yes, Doug?
So you take the children of a node and subtract their heights.
So usually you calculate the height bottom up. So you start at a leaf. So the height of a node equals 1 plus the maximum of the height of the left subtree. Whoops. I'm going to abbreviate it H. Max of the height of left and right subtree. So what you're doing in effect is a bottom-up discovery. You start at the leaves and work your way up. Okay. So here, we're working way at the bottom. Okay, Daisy is okay, but if we look at Binky's 2 subtrees, its left subtree is non-existent, so has a height of -1. Its right subtree has a height of 1, so that's a difference of more than 1. Here, if we look at it and do our numbering, okay, it's looking pretty good, except the problem is Fred has no left subtree. So the difference between Fred's left subtree's height and his right subtree's height is more than 1, and therefore it violates it. So you can see that even trees that look relatively balanced, like this one, can be not an AVL tree, and perhaps trees that look a little bit more unbalanced, like that one. So this one, which looks a little more unbalanced, is an AVL tree. This one, which does look more balanced, is not an AVL tree. Okay, but if you kind of look at it, you can see Fred isn't very balanced, right? So if you go in and drill down, you see Fred's not very balanced. Whereas if you look at this tree and you look at all the subtrees, actually all the subtrees are relatively balanced. So that's all we're going through with an AVL subtree. And it turns out we can prove that if we enforce this height condition, then we're guaranteed to always have order log n time, because we can prove, which we won't do, we might be done in 311, but it can be proven that roughly half the nodes are in the left subtree and roughly half the nodes are in the right subtree. Okay, so in order to rebalance trees, we have to do what are called rotations. Okay, so when we do inserts and deletes, we may have to rebalance the tree, and we redo it using a fundamental operation called a rotation. And we call it a rotation about a node. So here, we're going to do a rotation about D. So what's going to happen is B is going to swing down to become a left child of D. Okay, so that's what's happened here. B has swung down and become a left child of D. Now, in doing so, you can see that there has to be some subtree swapping. Because if B becomes the left child of D, D can no longer have C as its left subtree, right? So B is allowed to hold on to its right, I'm getting two. B can hold on to its left subtree, and D can hold on to its right subtree, which is what happens over here. But if B is becoming D's left child, then something has to happen to C. Okay? And it's very convenient. B is losing a right child. When B comes down here, B no longer has a right child. So B can adopt C. Okay, B adopts C. Okay, does this work? Do we still have a binary search tree? Well, we know that everything in A is less than B, and that everything in C is greater than B because it's in B's right subtree, and we also know that everything in C is less than D, right? Can we all agree that this inequality holds? If you think about it, you should agree that that inequality must hold. So if we look over here at this tree, what do we have? Well, we have everything in A is in B's left subtree, so we still have A less than B. And everything in C is in B's right subtree, so we certainly have the case that everything in C is still greater than B. B is D's left child, so what does that mean about the relationship between B and D? Yep. So we already knew that this relationship guaranteed that B was less than D, so it's perfectly fine for B to be D's left child. So we still have maintained our set of equalities. So that rotation is a valid one. Yes.
The whole idea of that rotation that like you change the tree, but this equality
This equality
stays the
still
same.
holds, exactly. So we're allowed to rebalance the tree, but we still have a binary search tree when we're done. Okay, so the rules, let me just put down the rules because you'll have to do these rotations in your assignment. So if D is a right child, so the first case is D is a right child. Okay, so in that case, what we're doing is we make B becomes D's left child, and B adopts C as its right as its right subtree. So this is the case where D is a right child. Okay, I am going to slightly change this, leaving B still like this. So now we're going to say that D is a left child. Okay, so what that means if I rotate is that B becomes D's right child, And what is D going to adopt in this case? Or what is B going to adopt, rather? B is still going to adopt C. Okay, so B adopts C as its left child. Okay, so the effect of it would be that, I'll just erase them again, that D would rotate up and B would rotate down, and C becomes B's left child. Okay, what I am going to do, I suggest that before you try to attempt the rotate method, that you do these two rotates that I have. If you go to, again, my lecture notes, you'll see the AVL rotation exercises. The last two slides give you two exercises with rotates, and I will put the answers up. I suggest that you try to do those two rotates before you attempt to actually implement the rotate method in Lab 10 or Lab A. Okay, so make sure you understand how to do the rotates. And I will see you